Hydrogen generation based on the biomass feedstock. Hydrogen can be produced both from non-renewable as well as renewable resources. Hydrogen from non-renewable resources. From natural gas. Natural gas is a hydrogen gas primarily made up of methane and is derived from fossil fuel. It also contains few amount of higher alkaline and non-hydrocarbon gases such as carbon dioxide and nitrogen, etc. Hydrogen is derived from natural gas through the following processes: steam reforming, partial oxidation, autothermal reforming. Steam reforming. In this process, methane is converted to carbon monoxide and hydrogen using steam and at a high temperature ranging from 700 to 850 degrees Celsius and pressure from 3 to 25 bar. Carbon monoxide formed is further converted to carbon dioxide and hydrogen through water gas shifting reaction. Partial oxidation. This process involves the partial combustion of methane to generate carbon monoxide and hydrogen. As this process is an exothermic reaction, external heating of reactor is not necessary. Autothermal reforming. This method is a combination of steam reforming and autothermal reforming. It uses oxygen and carbon dioxide or steam to convert methane to hydrogen. Hydrogen from coal. Hydrogen is derived from coal through various gasification processes such as fixed bed, fluidized bed, or end-drained flow. End-drained flow method is the most commonly used method since it maximizes the conversion of carbon to gas with limited formation of char, tar, and phenols. Gasification of the coal is represented by the following equations: carbon plus water plus heat, it produces carbon monoxide and hydrogen. The major drawback of using non-renewable sources such as fossil fuel for hydrogen generation is that it will lead to the emission of greenhouse gases, mainly carbon dioxide. Thus, the capturing of carbon dioxide released is an important step for a sustainable and eco-friendly production of hydrogen. In addition, the limited availability and fast depletion of non-renewable resources is also a major problem. Decarbonization. Decarbonization is an important step to be carried out if fossil fuel is used as raw material for hydrogen generation. The process involves the capturing and storage of carbon dioxide emitted during the production of hydrogen. The main aim of the process is to make hydrogen production more sustainable with zero emission. Hydrogen production from renewable sources. Using renewable sources such as water and biomass for hydrogen production is more beneficial than using non-renewable sources because it is easily available and renewable. The process is carbon neutral. Using renewable sources is more sustainable and eco-friendly. Following are some of the hydrogen producing methods involving renewable sources. Splitting of water. The process involves the splitting of water into hydrogen and oxygen using various mechanisms such as photoelectrolysis, that is photolysis, alkaline electrolysis, polymer electrolyte membrane electrolysis, and the thermochemical water splitting. Let us now discuss in detail about photoelectrolysis. Photolysis split water to hydrogen and oxygen using solar energy. It consists of a photoelectrochemical cell system which power the electrolysis process. A photoelectrochemical cell consists of a photoanode, cathode, and water as electrolyte. Photoanode is prepared by depositing a thin film of photocatalyst on its surface. When light hit on the photoanode, an electron is released along with the splitting of water to generate protons. The proton and electron move towards the cathode through electrolyte and external circuit respectively. At cathode, proton, that is hydrogen ion, are converted to hydrogen using the electrons. At photoanode, water split into hydrogen and oxygen and electrons. At cathode, hydrogen and electrons release hydrogen gas. That is, water is split into hydrogen and oxygen. Alkaline electrolysis. In alkaline electrolysis, KOH used as electrolyte. Following reactions are involved in an alkaline electrolysis cell. Electrolyte, water is converted into proton and hydroxyl ions. Cathode, 4 protons and 4 electrons convert to 2 hydrogen ions. Anode, 4 hydroxyl ion is converted into oxygen and water molecule plus 4 electrons. In total, 2 water molecule is converted into oxygen and 2 hydrogen. Polymer electrolyte membrane electrolysis. PEM electrolyzer uses an acidic polymer membrane known as proton exchange polymer instead of liquid electrolyte. At anode, water is split into oxygen, protons and electrons. Protons move to the cathode through the membrane, whereas the electrons move through external circuit and reach cathode. At cathode, proton ions are converted into hydrogens using electrons. Anode, water is converted into proton, oxygen and electrons. At cathode, protons plus electrons convert to hydrogen gas. In total, water molecule is split into hydrogen gas and oxygen. The thermochemical water splitting method. Thermochemical water splitting involves the conversion of water to hydrogen and oxygen through a series of chemical reactions at a specific temperature. The chemicals used for the reactions are retained at the end of the process, and this can be used for next round of conversion. Thus, this process is repeated as a cycle by utilizing only water to produce hydrogen. The following reactions represent iodine sulfur cycle, an example for thermochemical processing of water. Sulfuric acid at 850 degrees Celsius convert to SO2, H2O and oxygen. Iodine plus SO2 and 2 molecules of water at 120 degrees Celsius produce H2SO4 plus 2 hydrogen iodide. 2 hydrogen iodide to split into iodine and hydrogen at 450 degrees Celsius. In total, water molecule is converted into hydrogen and oxygen.